Today, we are opening the case file on what is without a doubt one of the biggest mysteries in the entire universe, dark matter. We're talking about a substance we can't see, we can't touch, but we know it's there because of the gravitational pull it has on, well, everything. So let's dive right into this cosmic detective story. To really get a handle on just how huge this mystery is, let's start with a really mind-bending question. I mean, we all know about stars and planets and galaxies, right? All that stuff is made of atoms. But what if I told you that everything we can see, everything we've ever observed, makes up only a tiny, tiny fraction of the cosmos? So what in the world is the other 85% of the universe's mass made of? The short answer is, we have no idea. A truly staggering 85% of all the matter in the universe is something else entirely. It's this invisible, kind of phantom substance that scientists have given the name dark matter. And it's called that because it doesn't give off light, it doesn't reflect light, it just exists. And figuring out what it is, that's one of the biggest challenges in all of modern physics. So you're probably wondering, how do we even know it's there if we can't see it? Well, the very first clue in this whole investigation popped up almost 100 years ago. Astronomers were looking at galaxies, and they noticed something really odd. The stars way out on the edges were spinning around so fast that by all rights, they should have just been flung off into deep space. The only thing that could explain it was if there was a massive, invisible halo of matter providing the extra gravity needed to hold the whole galaxy together. Okay, so the crime scene is the entire cosmos, and the evidence is pointing to some kind of missing culprit. Now, the investigation has been going on for decades, and through a ton of brilliant theoretical work, scientists have actually managed to narrow it down. Right now, there are three main suspects for what dark matter could actually be. So, let's bring in our suspects for the lineup. We're going to take a look at the top 3 particle candidates for dark matter. And what's wild is that each one comes from a totally different corner of theoretical physics. And, each has its own very unique profile.
And here they are. First up, we've got the WIMP. That's short for weakly interacting massive particle. We'll call it our heavyweight contender. Then there's the axion, this ultralight particle we're calling the ghost. And finally, the sterile neutrino, or the elusive sibling to a particle we actually already know about. The really fascinating thing here is just how different they are from each other, from super heavy to incredibly light, each with its own incredible backstory.
For a really long time, the WIMP was the prime suspect. As this quote gets at, WIMPs just fit so perfectly into these popular theories that go beyond our current understanding of physics. A big one is called supersymmetry, which basically proposes that every particle has a heavier superpartner. WIMPs could be those partners, and they'd have just the right properties to have been made in the early universe and account for all the dark matter we see today. All right, suspect number 2 is the axion. Now, this particle wasn't just invented to explain dark matter. It was actually proposed to solve a completely separate puzzle in particle physics called the strong CP problem. It's basically a deep mystery about the fundamental forces of nature. But here's the kicker. It just so happens that if axions do exist to solve that problem, they would have been produced in enormous numbers in the Big Bang, making them a perfect dark matter candidate. You gotta love a 2-for-1 deal in theoretical physics. And that brings us to our final suspect, the sterile neutrino. We know for sure about 3 types of neutrinos, but some theories suggest there could be a 4th, much more elusive sibling out there. This sterile version wouldn't interact with matter through the weak nuclear force like its siblings do. Nope, it would only interact through gravity, which would make it incredibly hard to find. And, you guessed it, an ideal candidate for dark matter. So, we have our lineup, but how do you actually go about finding these particles? This is where things get really interesting. Let's move on to the next phase of our investigation and see how scientists are trying to interrogate these cosmic suspects.
I mean, this is really the central challenge, isn't it? How on earth do you catch a particle that, by its very definition, barely interacts with anything at all? It's kind of like trying to catch a ghost with a butterfly net. You need some unbelievably clever and just unbelievably sensitive experiments.
The key takeaway here is that there's no single method. Scientists are using a multi-pronged attack. For a heavyweight contender like the WIMP, they build these huge, sensitive detectors and hope to see one just bump into a single atom. For axions, they use incredibly powerful magnets to try and basically trick them into turning into light. And for sterile neutrinos, they hunt for weird behavior in existing neutrino experiments. And this is a perfect illustration of one of those methods. This is the ADMX experiment, the axion dark matter experiment, and it's designed to hunt for the ghost. So inside that big device is a super powerful magnet and what's called a resonant cavity. The whole idea is that as dark matter axions from our galaxy's halo pass through, that magnetic field can convert a teeny, tiny fraction of them into microwave photons, which the experiment is then tuned to pick up as a very faint signal. It's basically an axion to light converter. Now, if you want to catch the heavyweight WIMP, you've got to go deep, really deep. Experiments like XENON and DarkSide are built in laboratories deep underground, often in old mines. And they do this to shield them from all the cosmic rays and radiation constantly bombarding us on the surface. They're trying to create an ultra-quiet environment where the faint whisper of a WIMP bumping into a single atom might finally be heard.
So what about the elusive sibling? Well, to try and find sterile neutrinos, we use absolutely massive observatories like IceCube. This detector uses a full cubic kilometer of pure Antarctic ice to look for high-energy neutrinos coming from space. Scientists then have to sift through mountains of data, searching for anomalies, like strange patterns of neutrinos disappearing or appearing that could only be explained by a fourth sterile kind of neutrino. So, after decades of searching with all of these incredible cutting-edge experiments, where does the case actually stand? Let's take a moment and evaluate the evidence, or lack thereof, for each of our primary suspects. Let's start with our one-time frontrunner, the WIMP. Its strength has always been that it just made so much sense theoretically. But the challenge is a big one. Despite years and years of looking with more and more sensitive detectors, we have found absolutely nothing. Zero. To make things worse, the Large Hadron Collider hasn't found any evidence for those theories, like supersymmetry, that predict WIMPs in the first place. Honestly, the case is looking a bit cold.
Next up in the lineup, the axion. Its biggest strength is just how elegant it is. It solves two massive problems in physics at once. But its defining trait, that incredibly weak interaction with everything else, is also its biggest challenge. I mean, detecting it requires pushing our technology to the absolute bleeding edge. It's a beautiful theory, for sure, but a really, really difficult one to prove. And finally, the sterile neutrino. Its strength is that it's connected to the physics of neutrinos, which we already know exist. It could even explain other big cosmic mysteries, like why there's more matter than antimatter. The challenge, though? The theory behind how they were made is really complex, and experiments have already ruled out large chunks of where it could be hiding. The room for it to exist is getting smaller and smaller. So where does all of this leave us? Well, as this source pretty much sums it up, no single suspect has been cleared and no single suspect has been convicted. The evidence is frankly inconclusive. And this is exactly why scientists are pursuing every lead at once, because the real culprit could be any one of them, maybe a combination of them, or maybe even something we haven't even thought of yet. And that brings us to the end of our investigation for today. The search for dark matter is genuinely one of the most compelling and important detective stories in all of science. It is a hunt that is pushing the absolute boundaries of our knowledge and our technology. And it leaves us with one final haunting question. After all this time, after all these incredible efforts, is the true culprit behind 85% of our universe still out there just waiting to be found? The case remains open.